Hello, and welcome to this talk on sparse convolutions on continuous domains for point cloud and event stream networks, work conducted at Queensland University of Technology in conjunction with the University of Queensland. My name is Dominic Jack, and I was lead author on this project. Image convolutions have been a cornerstone of many deep learning advances in computer vision. However, the research community is yet to settle on an equivalent operator for sparse, unstructured, continuous data like point clouds and event streams. This paper proposes one such operator, which is consistent with the mathematical definition of convolution and is continuous in input coordinates. We present an elegant implementation using only high-level linear algebra operations, which is both faster and more general than existing methods. We also demonstrate how pre-processing tools, usually reserved for data decompression and augmentation, can be used to drastically reduce training time for networks of such operations. We apply these ideas to point cloud and event stream classification problems, producing models which are performant with regards to accuracy, resource utilization, and speed. The convolution of a function can be defined as an integral of the product of that function and a shifted kernel. For images, our function is sampled on a regular grid, so any kernel with compact support need only be defined on a finite number of discrete points. The integral can thus be evaluated by summing scaled values over a sliding window. Convolutions on sparse continuous inputs require the kernel to be defined everywhere, but the idea is roughly the same. For each point in the output set, we identify neighbors in the input set and add scaled features. The difficulty with applying this idea to sparse inputs lies in the irregularly sized neighborhoods. Deep learning frameworks today mostly involve operations defined on regularly shaped tensors in order to take advantage of massive parallelism afforded by GPUs and other accelerator hardware. A common approximation is to fix the number of neighbors rather than the radius of the ball search. While this greatly simplifies the implementation, it introduces discontinuities. In this example, if node 2 were to move slightly closer to node 3, then it would supersede node 4 as 3's outermost neighbor. Of course, we aren't the first to propose using convolutions on continuous sparse inputs. Despite numerous papers identifying ball searches as a legitimate option for a neighborhood, we found virtually all point cloud models resorted to k-nearest neighbors. One apparent exception is PointNav++, which claims to use a ball search, though investigation of the source code reveals an implementation backed by a masked k-nearest neighbors, which exhibits aggressive truncation compared to standard ball searches and suffers from the same discontinuity. This leads us to the goal of this project, to develop an operator which is both consistent with the mathematical definition of convolution and continuous with respect to input coordinates, feature values, and learned parameters. To understand our implementation, let us first consider a standard 3x3 image convolution with a single input and output channel. Our kernel is parameterized by 9 learned parameters. Because convolution is linear, we can express this as a linear combination of 9 static basis convolutions. In doing so, the weights of the linear combination are what is learned, rather than anything in the convolutions themselves. Each one of these basis convolutions can be expressed as a sparse dense matrix product between a neighborhood matrix and the flattened image features. We can interpret convolutions on sparse continuous inputs in the same way. We express a learned convolution as the linear combination of multiple basis convolutions. Each one of these basis convolutions can be expressed as a sparse dense matrix product, where each sparse matrix will have the same sparsity pattern given by the ball search and values given by the associated basis kernel function. It can be shown that extending this to multiple inputs and output channels is simply a matter of replacing the rightmost scalar multiplication with a matrix multiplication. This gives rise to the exceedingly elegant formula shown, where n is a sparse matrix with the values dependent entirely on input coordinates, f is a feature tensor that can be propagated through a network, and theta is a tensor of learned parameters. The simplicity of this formulation has many benefits. First and foremost, it makes implementation straightforward. This not only reduces the maintenance burden on researchers, it also allows implementations to take advantage of subsequent optimizations from deep learning frameworks. As a concrete example, since our initial submission of this paper, TensorFlow has released limited support for compressed sparse row matrices, and switching our implementation to use this encoding resulted in a speed-up of almost 50%. Furthermore, the simplicity makes analysis of space and time complexity straightforward, leading to easily optimized implementations. For example, strided image convolutions are analogous to point cloud convolutions where the output cloud is a subset of the input cloud. In these cases, it is trivial to show evaluating the matrix products left to right requires less time and space than right to left evaluation. The opposite is true when the input set is a subset of the output set, in situations analogous to transpose convolutions. Now, most typical image CNNs are made up of alternating blocks of in-place and strided convolutions. We can mimic this architecture for sparse inputs. We note that each block requires a neighborhood search along with some index manipulations after batching. Since these are independent of learned features, they can be performed in a data preparation stage, either while accelerators are busy with the prior batch or cached offline before training begins. Pre-processing like this is commonly used for data decompression and augmentation, though to the best of our knowledge, this is the first work to demonstrate its use for architecture-dependent pre-processing. To facilitate rapid prototyping, we developed a standalone module for building metamodels, which simultaneously and incrementally build different networks for each conceptual layer. To evaluate the performance of our operation in isolation, we compared our implementation to benchmarks provided by FlexConv, an approach based on the same formulation that only supports k-nearest neighbors. Our implementation is written in pure TensorFlow and can support either ball search neighborhoods or k-nearest neighbors, making it strictly more general. All implementations pre-process neighborhoods and static kernel values offline. We outperformed our pure TensorFlow implementation by nearly 3 orders of magnitude in terms of both computation time and memory requirement. Compared to their custom CUDA implementation, ours can perform inferences almost an order of magnitude faster and some 60 times faster for a forward and backwards pass as required for training. To evaluate the performance of our networks, we considered the ModelNet 4D classification problem. Our model was designed with a kitchen sink mentality of ideas that have been shown to work for image CNNs, including a ResNet-inspired architecture with skip connections, ReLU activations, batch normalization, and dropout. Care was taken to ensure the entire network scaled with input size like n log n in terms of both computation time and memory requirement. But beyond that, the design process was based on simplicity and default parameter settings. Our implementation was almost an order of magnitude faster than the fastest publicly available implementation considered, and was able to run with batches with many millions of points before running out of memory on an 11 gigabyte GPU. Now, point clouds are not the only sparse inputs on continuous domains. To demonstrate the versatility of our idea, we applied our framework to the task of event stream classification. Event cameras are grids of independent pixel sensors that fire asynchronous events in response to changes in light intensities. They have many attractive properties, including very fast response times, high dynamic range, and low power usage. Now, it is straightforward to treat an event stream in XYT space as a 3D point cloud. At a very high level, we use the same approach as our point cloud networks above in terms of alternating in-place and downsampling convolutions. On a final level, we make 3 changes. Firstly, we subsample with a leaky integrate and fire model commonly used in spiking neural networks. Secondly, we define our kernel support such that each event's features are influenced only by previous events in a finite spatial neighborhood. Finally, we use kernels with a spatial factor analogous to image CNNs, scaled by an exponentially decaying temporal factor. These changes allow us to propose different implementations for each of training and inference. Our training implementation proceeds much the same way as it did for point clouds, with features of all events in a stream computed simultaneously, stream by stream. This allows us to express the manipulation in a relatively small number of large matrix multiplications. Our inference implementation computes features for each event in time order, using exponentially moving average updates. This allows for asynchronous inferences available at the moment the event is fired, and since it requires memory proportional to the number of pixels rather than the number of events, we can stream inferences indefinitely. We conducted experiments on a number of event classification datasets, achieving minor improvements over state-of-the-art on multiple small-scale artificial datasets, and a 40% reduced top 1 error rate for the significantly larger sign language recognition dataset ASL-DVS, where streams often have hundreds of thousands of points. To conclude, we have proposed an elegant implementation of convolutions for inputs on sparse, continuous domains, which is consistent with a mathematical definition, can accommodate irregular neighborhoods, and is continuous in input coordinates. It uses only high-level linear algebra operations, yet it's more general and runs up to 60 times faster than existing custom implementations. Combined with efficient data pipelining, we demonstrate our point cloud networks can train an order of magnitude faster and require less memory than competing methods with comparable results, and our event stream implementations achieve state-of-the-art classification accuracies. TensorFlow implementations are available at the link on screen. Thank you.